This question asks, in each set, identify which molecule is more acidic. So we've got 3 sets of molecules. And again, you can use the quantitative method or the qualitative method. In an example like this, it might be a little bit harder to use the quantitative method because there might be some molecules that are harder to look up. For example, molecule 2 in set number 1, that's not a pKa value I know off the tippy top of my head. But I can definitely use the qualitative method to sort these examples out. So I'm going to take that route when I go to solve this question. Set number 1, we have 2 molecules that are possessing aromatic rings, but the key difference is right here, what's attached. We have an alcohol and a thiol. So the real comparison here, when we're thinking about Cario, is not going to be charge, because they're both neutral, but atom. So one has an oxygen and one has a sulfur. When you go down the periodic table, the key determining factor is polarizability. So if you think about the sulfur atom versus the oxygen atom, the sulfur is more polarizable because it's able to spread its charge out more. And so that stabilizes it. So whenever you have a sulfur or a thiol versus an alcohol, the molecule that has the sulfur is going to be able to stabilize the conjugate base better. Okay, so the conjugate base would look like this, where that negative charge is going to be spread out better on the sulfur atom versus the less polarizable oxygen. All right, let's take a look at question number 2, or set number 2. Here we have 2 molecules where if we draw out their conjugate base, we're going to have O- here versus another O-. So if we're thinking about Cario, they're both negatively charged. They both have the negative charge on the same atom, oxygen. So here, the next thing to do is look at resonance. So in resonance, that's again going to be the ability of us to spread the charge out. In this example, there is no resonance because there aren't any neighboring pi bonds or positive charges. However, we can spread the charge out multiple times for molecule number 3. So it does have resonance. Resonance is stabilizing. So that means that we're going to have a more stable base with the resonance. So that means that molecule 3 is going to be more acidic because it has the more stable conjugate base. Okay, let's take a look at our last set number 3. This is a little bit of a harder example. In this case, let's think about what the most acidic proton is in each instance. Molecule 5 is symmetrical, so the only proton really that we can take off is that one. And so if we think about its conjugate base, we would have this molecule, and then its resonance contributor. Molecule 4 is a little bit more difficult because it has multiple protons, in theory, that could be deprotonated. If we take off the proton that is on the far right, we get an example that's very similar to molecule 5. However, if we take off the proton that's in the middle, right here, we get a few more resonance contributors. Okay, so we could have resonance going to the left, or we could draw resonance going to the right. And so molecule number 6 has more resonance than molecule number 5. And so because of that, and because the atoms are all similar, they're both spreading the charge out onto oxygens and carbons, we can say that more resonance contributors in this instance are going to lead to a more stable molecule. So molecule number 6 is going to be more stable as an anion versus molecule number 5's anion. So that means that molecule 6 overall is more acidic. All right, so let's take a look at our answer choices. So we said that in set number 1, molecule number 2 was the most acidic. So I'm going to cross off A, C, and D from our answer choices. Next up, set number 2, we have molecule 3 is the most acidic. So we can already narrow our choice down to the correct answer. To confirm, set 3 says 6 is the most acidic, and that is also in line with what we determined. So the answer to this question is E.